Welcome back. In this video, we're going to be taking a look at the simple harmonic motion that occurs after an inelastic collision between two objects, one of which is attached to a spring. Like the last video, we're going to be using some concepts from Physics 2a, so keeping all this in mind, go ahead and read through the problem statement. As the problem states, we have a situation in which a block is attached to a spring. From beneath, a wad of putty is shooting towards the block and then it sticks to it, so when a collision occurs. This entire system consisting of the block and the putty then is set into motion, and because it's attached to a spring, that motion is simple harmonic motion. We know a couple aspects about this, the stiffness of the spring, the masses of both the putty and the block, and then the initial velocity of the putty before it hits the block. And the first thing we're asked to find is what is the equilibrium position of this block before any of the collision occurs. The second thing we're asked to find is what is the equilibrium position of this system. And then the third thing we need to find is what is the amplitude of the resulting simple harmonic motion. So let's go ahead and proceed with the first couple parts. And what we're asked to find here is an equilibrium position. Keep in mind these are static quantities. So even though collisions are occurring, dynamics are happening here, we're looking at quantities that don't depend on any of the dynamics. All it depends on is a balance of forces. In particular, if you use Newton's second law and set A equal to 0, then you can solve for the missing extension just by using balance of forces. So I want you guys to do that now. Draw a free body diagram, write down the forces, write down the statement of Newton's second law, set A equal to 0, and try to solve for this quantity before the collision has occurred and this quantity after the collision has occurred. Take a minute to do that now, and then we'll come back and continue the problem. If I draw the free body diagram for the situation before the putty has hit the block, well, on the block you just have two forces, the force of the spring pulling upward and the force of gravity pulling it downward. To reiterate, this is in equilibrium, so the acceleration should be 0. So if I write down Newton's second law, find that the sum of the forces should equal 0. And if you notice here, I wrote that the positive x-axis points down. And you can choose that however you want. I've just noted that in this way because we're only dealing with quantities that are over here. So I just kind of made the positive x-axis point down. So this is a positive force. This is a negative force. So you have the weight minus the spring force equals 0. The weight is the mass times gravity. The mass in this case is just the mass of the block, which is 400. So you have big M times G. And then the force of the spring is always the extension times the spring constant. The extension in this case I've defined as delta x EQ sub b, where b is for before the collision occurs. So it's the extension, which is that quantity, times the spring constant. And we know everything here except for this quantity right here, so you can solve for that very easily to get 7.84 centimeters. Right, now if you do the same thing for the situation afterwards, we're looking at equilibrium here, so again we're going to follow the same process. Just look at the spring force and the gravitational force. In this case, all that's changed is that the gravitational force is increased because you're dealing with both a block and a piece of putty, so the mass is a little bit more. So in this case we have m plus m times g, where this is the mass of the block and that's the mass of the putty, should equal, or minus delta x EQ sub a for after. And the spring constant, as in the last problem, the spring constant is the same. It's a constant of the system, so all it depends on is what is the spring made of, not how it's moving or what's attached to it. So it's going to be 50 still. Solving this for the equilibrium extension, we find that if this system is in equilibrium, it's going to be extended a distance of 9.80 centimeters. Okay. Right, so those answer the first two parts of the problem. The last part of the problem says what is the amplitude of the resulting simple harmonic motion once this putty has hit this block and this thing starts to execute oscillatory motion. Now in the last problem, if you recall, we had something kind of similar. There was this kind of, it was kind of a reverse collision. Two things flew apart, and then it started to execute simple harmonic motion. And if you recall from that problem, the way we found the amplitude was by subtracting where the thing started with the equilibrium extension. In this case, that would just be, it's starting at 7.84, and then the equilibrium is 9.8. But that's actually incorrect. So let me write that up here. The amplitude does not equal that value, the absolute value of that. Right? It's not just the starting position minus the equilibrium position. And I want you guys to kind of figure out, take a minute and find the faulty reasoning with that. Why can't we do this like we did in the last problem? What's different about the situation? Take a minute, think about it, and when you think you come up with an answer, restart the video and we'll continue the problem. Now the reason this equation is incorrect is because, well, the amplitude is defined as the distance between the equilibrium position and either the point where the block is at its max compression or where it's at its max extension. Now in this case, this is kind of somewhere in between. And to show you that, let me just go ahead and actually kind of indicate where these points are. The equilibrium position before the collision has occurred is of course where the block is situated because it is in fact in equilibrium. However, afterwards, the equilibrium position in this situation is a little bit lower. It's a bigger number, so it's further from the attachment of where the spring is to the ceiling. So it's somewhere down here, kind of. And this point right here is not a point of max compression. And the reason we know that is because when this collision occurs, this is an inelastic collision. So whatever velocity this putty had will now be transmitted to a velocity of the full system. And you can solve for that by using momentum conservation, just like we did in Physics 2a problems. Importantly, though, because this mass is not an infinite number, that velocity will be non-zero. So it's going to set this guy into motion immediately after the collision occurs, which means it's going to be going up with a certain velocity at this point, and it means that it can't be at its max compression. Because at max compression, its velocity has to be zero. It's got to be turning around. So at this point, we have to have the velocity equals zero. And so this is somewhere in between. And the reason that this can't be true is because this distance is not the amplitude, since the amplitude occurs when the velocity equals zero. So we actually had to find a different way to solve this problem. So again, this is not the amplitude because it's not a turning point. Turning point meaning max compression or max extension. And the method we're going to use instead is the conservation of energy. And the reason we can use that is because energy is in fact conserved in this problem. Energy is conserved in any situation in which there's no dissipation. So there's no friction, and we haven't said there's any friction, or the friction is negligible, we're not going to worry about it. If that's the case, then the total energy at any given time will be the same at all other times. And the total energy consists of both kinetic energy and potential energy. So instead we're going to use energy conservation. And the reason this is useful, so while this may be true, it may not be useful, but it is useful in this case because if you know the energy at any particular time, the total energy, then you can equate it to the energy at any other time, and hopefully that can allow you to find missing quantities. It turns out we do know the energy at a particular time. We know the full energy at this time. And the reason is because the energy is composed of three different terms in this case. The kinetic energy, which, well, we don't know the velocity yet, but we can find it using momentum conservation. So we have the ingredients to find the kinetic energy. It also consists of the spring potential energy, which only depends on how far the spring is extended, which we know. It started out at that much, so that's how much it's extended at that time. So we know the spring potential energy, and we also know the gravitational potential energy because we know where the block is. So we actually can find the full energy at this time, and that means the total energy at this time will be the exact same, but it'll be divided differently between its kinetic and potential energy components. So if we set those guys equal, hopefully we can solve for the amplitude. Because you see at this moment here, it's at its amplitude, so the A will enter the equation, and hopefully we can solve for it. So let me write this as the initial energy equals the final energy. And we just want to choose the 2 points. So the 2 points we're choosing are right after the collision occurs, that's our initial point, and the final point is right at max compression. That's a good point to use because it has the amplitude in there, and also importantly, the velocity is zero, so the kinetic energy term drops out. So if I write this out in terms of all its terms, each side is going to have a kinetic term, it's going to have a spring potential term, and it's going to have a gravitational potential term. And what I want you guys to do is find out the form of all these terms. Some of them may be zero. The ones that are not zero, find the form of them. And they're going to be in terms of the following quantities. They're going to be in terms of delta x's. They're also going to be in terms of A. Let me just point out here that A is this distance. and they're going to be terms of the masses, so be very careful about what the proper mass to use is here. You have two masses. And you may also have to use a spring constant. So all these quantities are going to enter in here at some point. So I want you to get an expression for all these guys. And I will just say real quick that keep in mind that the spring potential energy, in case you don't remember, is 1/2 K times the extension, which is called delta x. So whatever the spring is extended squared times 1/2 times K. And then we also have to assign our points of zero gravitational potential energy, which is our choice. Just to make our answers all equivalent, let me go ahead and sign that right here. So I'm going to assign this right here where UG equals 0. Right? In other words, the point of the equilibrium extension after the collision has occurred. So this is where UG equals 0. So anything above it will have a positive gravitational potential energy, and anything below it will have negative. All right, so keeping all that in mind, try to get an expression for all these terms, and we'll come back and compare our answers and finish up the problem. Our initial point is right after the collision has occurred, so let's talk about the energies right after that point. So the kinetic energy is 1/2 mv squared, v is vi. Careful, m is the full mass of the system, so you've got to add all those masses up. Okay. The spring potential energy, that's going to be 1/2 k times whatever the spring is extended at that point. In other words, this distance that is extended. This distance, it starts out at delta x EQB. So that's how much it's extended right after the collision occurs. The gravitational potential energy is going to be mg times, and again, m is the full mass, times the height above the 0 point, which we set here. This is a convenient point. Now, how high is it above that? Well, this distance is going to be, well, if you take a look at this, delta x EQA is the full distance, and then delta x EQB is this much. So if you subtract this minus that, you should get this remainder. And keep in mind, I'm subtracting the after minus the before. The after is actually bigger because the x-axis points down, even though it's lower. Okay, so it's going to be EQA minus EQB. That'll give us a positive number, which we should have. It's a positive gravitational potential energy because we're above the 0 point. So it's going to be A minus B here. Now, after the collision occurs, the kinetic energy is 0 because we're talking about the point where it's at max compression. By definition, that's a point where the velocity is 0, so the kinetic energy is 0. The spring potential energy, again, is 1/2 k times however much it's extended. In other words, this distance. That distance is the entire distance minus A, so delta x EQA minus A all squared. And then the gravitational potential energy is mg, or m is our full mass again, times the height above the 0 point. This is exactly A above the 0 point. All right, so we have our equation. Now let's see if we can solve for what we need to find, which is A. The only thing you'll see here that you're missing is the initial velocity. So to find that, of course, we have to use momentum conservation after the elastic collision has occurred. So I want you guys to do that on your own. Find out what VI is. You can actually get a number for that because we know the initial velocity. So set the initial momentum of the full system equal to the final momentum of the full system right after the collision has occurred. Solve for VI, and then we'll come back and finish up. Momentum conservation says that the full momentum of the system right before the collision occurs equals the full momentum after the collision has occurred. Right before the collision has occurred, we have momentum from both the putty and the block. From the putty, its momentum is its mass times its velocity. Likewise for the block, it's its mass times its velocity, which is 0. And then after the collision has occurred, now we have a single object whose mass is a combined mass, and its velocity we've denoted as VI in our problem. Okay? So everything here you know except for VI. You can invert this equation to solve for VI of 0.6 meters per second. And then plugging that in along with everything else in this problem, you should find that the amplitude of the resulting harmonic motion is about 6.31 centimeters. Okay. So I'll stop the problem there. If you have any questions or concerns about the algebra involved in solving this equation, it's written in a little more detail in the attached solution. So take a look at that. And then there's a summary on the next page. Take a look at that, and we'll see you next time.